Good afternoon. So, usual housekeeping, folks. Any questions about this, ask them through the app. We may have time to answer them at the end. And yeah, welcome. This is me, Dylan Beattie. I run Versatile, which is a training and a strategy consultancy company. I'm going to disconnect from the Wi-Fi in case something is going to keep sending me important little bouncing messages throughout this session. There we go. There are no live demos in this talk. It'll be fine. I'm a Microsoft MVP. I run the London .NET user group. Now, I know there's some folks in the room who think this is a Java conference, but apparently there's also a lot of folks in the room who think this isn't a Java conference. So I hope I'm not offending anybody by flying the .NET flag here. But the thing that I'm sort of maybe best known for is I once invented a programming language as a joke, and the internet liked it and implemented it, and it became a joke with a reference implementation and a formal test suite. It is the programming language called Rockstar. And if any of you want to go on LinkedIn and apply for all those sweet Rockstar programmer jobs, you can program them in Rockstar. And the great thing about it is all your programs are also heavy metal songs. So even if it doesn't compile, you can still sing it and enjoy programming that way. Now, the title of this talk is loosely paraphrased from a quote from the movie Apollo 13. Now, spoilers ahead, but A, it's based on a true story, and B, it's been out for like 30 years. It's the story of the Apollo mission that was on the way to the moon. They had an explosion, and there was this whole, are we going to be able to bring our astronauts back alive? And there is this famous strapline for the movie. This guy, Gene Kranz, so this is the actor Ed Harris, playing Gene Kranz, the NASA mission director. And at one point in that movie, he comes out with this fantastic line, failure is not an option. Now, he didn't actually say that, or he did, but he didn't say it until 1995. This is the real Gene Kranz, who was the mission director on Apollo 13, and he said that line in an interview with the people who wrote the movie. And they kind of looked at one another and went, that's it. That's the line we need on the posters for the movie and everything. And he liked this so much that he then borrowed his own quote back and made that the title of his autobiography. But let's talk about failure is not an option there for a second. Now, Apollo 13, the Apollo program, used a launch vehicle called the Saturn V. The Saturn V was engineered to a 99.9% reliability. It had 6 million separate components, which means that on a successful mission, they would only have 6,000 failures. Failure's not an option? Well, it sounds like 6,000 failures is very much an option. Now, the success of the Apollo program was down to lots and lots of incredibly smart people. And one of those people was this lady, Margaret Hamilton. She ran the team that wrote the software that took Apollo to the moon, the main Apollo guidance system. And she has this wonderful quote. She was the first person ever to refer to software engineering and systems engineering. And she said, you begin to think in terms of modeling all these things as one system. Part is software, part is peopleware, part of it is hardware. She was absolutely like, you are not going to give me a rocket and expect to install my software on it and off you go. We are going to be involved at every step of this process. The life support system, the hydraulic system, the guidance system, the computers, all these things will be evolved together in parallel. That way we can ensure that the system itself is going to work properly. Now, Apollo also has what I think, if any of you just watched Sanders' talk earlier this afternoon about doing Agile without doing user stories and stuff, I'm kind of on the fence about that, but I do think that this is the greatest user story of all time. To land a man on the moon and return him safely to the Earth. Now, if Kennedy had said land a woman on the moon and return her safely to the Earth, he would have made everyone's lives much easier for all kinds of reasons, but it was the 1960s, and anyway, and they did. The Apollo program successfully landed human beings on the moon, 1969, July 16th, well, actually July 20th is when they landed. That's when it actually got delivered. Or did it? Because he said, return them safely to the Earth. So when did Apollo actually deliver? What was their definition of done? Was it when they set foot on the moon? Was it when they planted the flag? Was it when they took off? Was it when they landed? Was it when they got out of lunar quarantine 14 days later in case they'd come back with moon diseases? Because everyone always forgets the other parts of your definition of done to successfully deliver the outcome of your system. Now, Apollo 11 was a huge success, a triumph of human endeavor and engineering. A few months later, they launched the second mission, Apollo 12. And Apollo 12 had a little bit of a problem because about a minute after liftoff, it got struck by lightning twice. Now, I want you to imagine this for a second. You got you and two other people crammed into something the size of the back of an Uber. You are on top of 2 million liters of the most explosive fuel humankind has ever come up with. You are supposed to be on your way to the moon. There is a massive bang, a catastrophic noise, and all the lights go out. Now, your first thought is, we're probably not dead, because if we were dead, we wouldn't be terrified. Your second thought is, what the hell is going on? What just happened? Now, if you take a look, this guy, John Aaron, he was one of the people who worked on the guidance systems for Apollo. And he had an idea. NASA had not simulated what happens if the 2 million liters of explosive rocket fuel gets struck by lightning, but they had simulated pretty much every failure scenario they could think of. And John Aaron is looking at all this telemetry coming down. He's talking to, or the capsule communicators talking to the astronauts, and he's like, the ship is clearly still going. The rockets are still firing. The lights have all gone dark. Maybe everything is fine except the dashboard. Maybe what's happened is the electrical strike, the lightning strike, has knocked out the signal conditioning equipment, which is what they call the dashboard. Now, this famous picture of Margaret Hamilton, if you look at what's up above her head, she's sitting underneath the main control console for the Apollo capsule. And down the bottom right, there is this little layer of switches, little panel of switches, and one of those, by the way, I have no way what squelch A and squelch B do. I couldn't find that out. But this thing here, power, SCE, signal conditioning equipment, has two settings. Normal and auxiliary. It has a backup. John Aaron says to them, try setting the SCE to aux. And they flick the switch, and all the lights come back on. Everything lights up. And there's got to be a point where they're looking at each other going, are we really going to go to the moon now? So they do a couple of orbits of the Earth, and they're like, this seems fine. You know, everything checked out. Off we go. Let's go to the moon. And they did, and Apollo 12 landed, and Pete Conrad became the first person to play golf on another planet, which is kind of cool. So if failure was not an option, why was there a backup system? The answer is there were backups for everything. The Apollo 13 mission had an engine failure on launch. It launched with 5 engines. That's why it's called the Saturn V. One of them didn't light. It's all right, they got 4 more engines. It had a backup crew. If you remember the scene in the movie where one of them can't go to space because he might get measles, it's all right, they've got crew backups. They had this thing. This was the Apollo launch escape mechanism. Now, this was never used, but worst case scenario, if the spacecraft actually exploded on the pad, in theory, this thing would take the command capsule off the top and parachute the astronauts down safely. Now, it was never used because the Apollo program, or the Saturn, has the distinction. It's the only rocket that has never exploded on a mission. It's the most successful rocket that we human beings have ever built. And to understand the context of failure is not an option, you need to understand what was actually going on. At that point in the story, they have reframed the objective. Apollo has succeeded. They have beaten the Soviet Union to the moon. Tick. The system has delivered its outcome. Apollo 12 has been up. They're sending Apollo 13 to do more propaganda, more science, more research, basically just to prove they can do this thing again. The mission parameters get redefined. They can't land on the moon. That is gone. They're like, now the objective is to bring our people home, make sure they get back safely. And so in that context, we've never lost an American in space. We're not going to lose one on my watch. Failure is not an option. That's the context they're talking about, the successful outcome of a system. Now, Apollo 13 was a successful outcome. They brought the astronauts home. Apollo 14, 15, 16. By Apollo 17, everyone was getting bored. There's another quote in the movie. They made going to the moon look about as exciting as taking a trip to Pittsburgh. Apollo was expensive, and it didn't really do very much. They walked around, they took photos, they came back, and Congress was starting to get twitchy about the cost. The public had sort of lost interest. They'd beaten the Soviet Union. But NASA had something else coming up. The Space Transportation System. We call this the Space Shuttle. NASA do not call it the Space Shuttle. It's like Baby Yoda. The whole world knows it as one thing, but officially it's called the Space Transportation System, which has 3 components. It has the external fuel tank, it has the orbiter, and it has what are called the solid rocket boosters. Now, the shuttle flew with a whole bunch of technology which had been validated and tested on the Apollo missions, but it also flew with a whole bunch of new stuff that had never been flown on a spacecraft before, including the first fly-by-wire computer guidance system used in space travel. Now, to understand the way they engineered the space shuttle guidance system, we need to understand how computers go wrong. If you open up your laptop and you say, oh, I want to go to the New York Times, I want to look up the news, I want to see what's happening today. If it doesn't work, there are 3 different ways that it can fail. One is you get an error message straight away. The machine says back to you, that didn't work. Here is some information about what failed. You're going to need to do something different. You might, loading, and eventually you or your browser or your internet provider or your cellular network is going to go, no, we give up. Nothing's going to happen. Request timed out. Something should have happened by now, but it didn't. But what if you open the New York Times and you get SpongeBob invades Luxembourg? Now, that looks like the New York Times, but you're looking at it, you're thinking, I don't entirely trust that. Maybe something isn't right here. And so what you do is you go and validate that against another authority. You get your phone out your pocket, you're like, well, my phone says that Biden signed off on a tax deal. So you check your tablet and you're like, well, that also says Biden signed off on a tax deal. So A, I don't think SpongeBob invaded Luxembourg, and B, something is wrong with my laptop. I cannot trust the results I'm getting from the browser on my laptop. Maybe it's malware, maybe it's DNS, maybe my kids have been messing with it, but for whatever reason, you can no longer trust that. Now, what if your laptop says SpongeBob invades Luxembourg, so you pull out your phone, that says Mexico won Eurovision. You get your tablet out, it says NASA's found the Brexit opportunities on Mars. At this point, you're like, this is a systemic failure of the whole mechanism of online news. So if you want to know what actually happened in the world that day, you're probably going to need to find something that doesn't rely on the internet, like a printed newspaper or switch on your TV or something. And all of this was taken into account. The space shuttle flew with 5 of these. This is an IBM AP101 mainframe in a box. It's a thing about this big. And the shuttle had 5 of these on board. Now, 4 of them were identical. They were identical hardware from the same supplier, built by the same people in the same factory, running 4 copies of the same software with the same timing clock, the same input, the same output. The idea was that these would always give exactly the same result at every point in the mission. And so at any point, if one of these suddenly gave you a discrepancy, you could realistically conclude that that one had developed a problem. There was a hardware fault with that unit, or it had been zapped by a cosmic ray or something. You could take that one out of the loop. You still had 3 left. But then if you lose another one, okay, well, this is bad, but we got another one. Then you're down to 2. And if one of those 2 goes different, now you don't know what to do, because you don't know which one of those is correct. So the Space Shuttle mission abort criteria said if they lost 1 computer, they had to turn around and come home, because if they lost another one, they'd be down to 2, and then if they lost another one, they'd probably have a problem, which is pretty conservative. You know, that is some serious failure resilience engineering. But they also anticipated the scenario that all 4 of these computers suddenly go haywire at the same time. And so the 5th computer, same hardware, but it ran a completely different set of software. They gave the same specification to a different supplier and said, we need you to write us a second copy of the software, or rather a second implementation of the same spec, that solves all the same problems in a different way. Because what their analysis, their risk calculation had showed is even if both of these implementations had a catastrophic bug in the software, it wasn't going to be in the same place. So even if the primary system had a catastrophic failure and the secondary system had it, it wasn't going to happen at the same point. So when that one went over, the failover computer would almost certainly be able to kick in and bring the astronauts and the orbiter safely back to Earth. Now, the first few shuttle missions, they carried a 6th, and the 6th wasn't loaded with anything. It was a spare. And the idea was that if they got into orbit, they had a computer failure, maybe it would be a good idea if they plugged in the spare computer, they installed the software on it, they copied all the telemetry across. You know, it's like reinstalling Windows, only you're doing it in orbit around the Earth at 250,000 miles an hour. It's like, you know, is that anyone's idea of a good time? But what happened is after 4 or 5 missions, they went, well, we haven't used the spare. And it's quite heavy, and sending heavy things to space is really expensive. And we could be using that payload budget to launch satellites or run experiments or do research. And so they stopped carrying it. Now, this is indicative of a problem with human beings' attitude to risk. It hasn't gone wrong, therefore we were probably being too careful. Is anybody here a nervous flyer? Do any of you folks out there, you don't like being in an airplane because, you're in the sky in a metal box and they're serving you gin and tonic and pretending you're in a restaurant, but you're not. You're 40,000 feet above the ground doing 600 miles an hour, and it's a deeply, deeply uncomfortable place for human beings to be, and then you land and you go, it's over, fine, I can relax now, and you get outside the airport and you get in a taxi. You are way more likely to die in the taxi, because taxis kill more people per hour of travel than aircraft do by orders of magnitude. But that's not how we think about the world, because to us, to most people, a taxi is familiar. It's everyday. It's a car. You drive your car every day. How bad can a car be? Whereas air travel, that's unfamiliar. That's exotic. And so when you think about how dangerous is driving, you think, well, I drive, no big deal. Think about how dangerous is flying. Your brain goes, well, there was that plane crash on the news, and there was the thing about the Boeing, and there was the thing about this, and the thing about that. And so you catastrophize, because your mental model of that is based on storytelling, not on lived experience, because you don't have enough lived experience for it to feel familiar. Now, the same thing is true of deploying, configuring, upgrading systems. How many of you ever go into like a big customer demo and like 10 minutes before you go in, Windows says, hey, update's available. And you go, yeah, YOLO, Windows update before the customer demo. We don't do that, right? Because Windows Update changes things. And when things change, we don't know what happened. One of the settings may not work anymore. There might be a network port that suddenly you can't get access to anymore. We don't like unfamiliarity. Novelty introduces unfamiliarity, and that can be risky. That can be scary. Now, the vast majority of engineered systems have something called a bathtub curve. And this is just saying that when systems are young, they go wrong a lot. And then they enter the kind of middle part of their life cycle where most things are kind of fine. And then at the end of their life cycle, they go wrong again. Now, in mechanical systems, this is because when a car comes off the production line, there's maybe a couple of bits that weren't installed properly, or a manufacturing defect. You take it back to the shop, you get those fixed. Your car runs happily for 5, 10, 15 years, but eventually you get to the point where things just start to wear out, and it's not worth replacing every single bit of it. Software doesn't wear out. But what happens with software is we have the early life cycle failures. Now, if you launch at this point, that's Windows Vista. And as you find these failures and identify them, they get fixed. And if you wait till most of them are fixed, you get Windows 7, which is the same product with another 2 years of finding problems and fixing problems. Then you get what are called random defects. Just no system is perfect. They all have little quirks and edge cases that crop up over time. And then finally, you get to the point where it wears out, if you like, what we call the late life cycle defects. Now, in software, the reason we get late life cycle defects, in my experience overwhelmingly, is when we launch a new system, everyone is on it. They're sending a, hey, new system's launching tomorrow. Keep an eye on it. Anything weird happens, please let us know. You're looking at your dashboards and your telemetry and your tests and everything. Then it kind of settles down. Maybe you do a little bit of maintenance. But eventually you get to the point where somebody says, oh yeah, the replacement system's coming. And so your focus shifts away from maintaining the status quo to developing the system which is supposed to replace it. Does anybody recognize this building here? Berlin Brandenburg Airport, Willy Brandt Airport. Does anyone know when Brandenburg Airport was going to open? 2008 is when they said, yep, 2008, it's good to go, they will open then. You know when it actually opened? 2020, maybe 21. 2020, but the pandemic knocked it back by a year. Now, this means that, and I've been to Berlin several times, both before and after they finally opened the new airport. And before they opened the new one, if you wanted to get a flight out of Berlin, you would get the metro as far as the place with the lawnmower shop. And then you'd cross the street and wait in the rain for the bus that would take you to Berlin-Tegel Airport. And you'd be thinking, this is the major airport of one of Europe's capital cities. Why do I have to get the bus? And I bet you every 3 months somebody would say, we have to extend the metro to Tegel, and someone else would go, no, we don't. Brandenburg is opening soon. We should invest in the new system. And new systems very seldom get delivered on time, and so the old systems get neglected because everyone is focused and excited on the new one. And so we get to this point where people's perception of risk, people's perception of where we should be investing our attention, the familiar things start getting ignored. Now, the Space Shuttle computer system never had a problem. It flew flawlessly for the entire lifespan of the shuttle program. But there were a bunch of other things in the Space Shuttle mission abort criteria. The thing which says you got to stop and come home right now. You could not launch the shuttle if it was raining, because, I don't know, it wasn't waterproof. You could not launch the shuttle if the wind was above a certain speed. You could not launch the shuttle if the temperature was above a certain level. But the Space Shuttle launched in Florida. And people don't think of Florida as somewhere that gets cold. And so there was no minimum temperature in the launch abort criteria. In 1984, they launched the shuttle when the temperature outside was 13 degrees Celsius. And they went around all the suppliers and said, it's a little bit cold out there for Florida. What do you think? And the suppliers all went, well, we don't think it's a good idea, but we are not going to be the people who vetoed the launch. So please make a note that we said it was bad and then do it anyway. They all did this. This is NASA Management 101 in the 1980s. It's a bad idea, but we're not going to stop it, so do it anyway. A year later, 1985, the temperature outside was 10 degrees. And they kind of went around the room and was like, well, 13 was all right. So I guess maybe we're being too cautious. Maybe 10 degrees will be fine. 1986, the temperature outside was 6 degrees. Space Shuttle Challenger exploded, killed 7 astronauts on board. Because of this attitude of gradually decreasing strictness. Now, one of the contributors to the investigation was this guy, Richard Feynman. He's a Nobel Prize-winning physicist. And his comments were published as an appendix. NASA didn't like what he had to say because his observation was that mismanagement and an attitude to risk was the primary factor here. He had a quote in this. He said, the certification criteria use gradually decreasing strictness. The argument that the same risk was flown before without failure is often accepted as an argument for the safety of accepting it again. Now, if any of you has ever had the seatbelt on your car go wrong, and you get in your car and the first time you drive with no seatbelt, maybe you're just taking it to the shop to get it repaired, it's terrifying, right? Because I know you've got to wear a seatbelt or you'll die instantly. This is what we've all been taught to believe. And you drive around the block and you're like, well, I'm not dead yet. Maybe big seatbelt is making the whole thing up. And it's frightening how rapidly you kind of recalibrate your expectation. Because the point about seatbelts is they're not designed to use when you're driving. They're designed to use when you're crashing. That's what they're for. And most of the time, we are not crashing. We just can't guarantee that we won't. Now, working in modern cloud software, I've been building software since the days when if someone said, hey, we need to spin up a new web server, the delivery time would be 6 to 8 weeks. And when it came, you needed 2 people to help you carry it up the stairs. And now you can go onto Azure or AWS and you can go, hey, cool, let's run the right-click, new server, boom, done. It is almost to the extent, somebody once described it as, it's the cloud is like not having to buy fire extinguishers because you can get them delivered in 30 seconds when you smell smoke. Which is kind of true. We don't have to do this level of tolerance engineering because it is so easy to scale systems on demand. Just, when the building does catch fire, you probably need to make sure that the delivery is going to work and you know what to do with the fire extinguisher when it gets there. And we can build systems where we got proxies going to geographically distributed load balancers, and we got web farms, we got active replication. Like literally you can design a system so if the whole of North America goes away for a bit, you'll probably be fine until it comes back. You know what the single point of failure that has taken down more cloud architecture than anything I've seen is? It's the limit on the MasterCard that's used on the Amazon account. Because for a long while, before they sort of figured out maybe this isn't a good idea, you could go on AWS, you'd be like, yeah, give me a server, give me a database, give me a message queue, give me this. And it'd be like, yeah, I'll just put this on the same Amazon bill that you used to order your ebooks. And then it would try and put a payment through, and it would go, oh, well, now you have no money, so we're going to just stop all your services. And the reason why developers don't think about that is because we don't think of credit cards as our responsibility. The developers, the architects, QA, product ownership, we're like, yeah, well, obviously we're going to design the database. Obviously we're going to design the schemas and the failover and the monitors, the dashboards. When it comes to what's the limit on the MasterCard, we're like, oh no, finance. That's their problem. That's not part of our remit. And this is a failure of systems thinking. It is us focusing on the part of the system which feels like our responsibility and not taking that step back and going, well, hang on, like there's the software, but where's the hardware? Where are the peopleware? Where's the moneyware and the cash and the user experience and all of these other things which contribute to whether our customers are going to say that what we delivered that day was successful or not? Now, the biggest mistake that we can make as developers and engineers is to pretend that it is going to be fine, because the failures that make headlines are all characterized by a sort of an arrogance on the part of the people who created them of going, we don't need to worry about that. It's going to be fine. It was fine last time. We're being too cautious. YOLO, let's just go and do it. In 1995, the Post Office Limited, this is the company who run all of the high street post office facilities in the UK, they built a new IT system. They subcontracted it to Fujitsu, who subcontracted it to a bunch of other people. The system was codenamed Horizon. It cost something like £10 billion or some ridiculous amount of money. They ran a pilot system on half a dozen branches. They went, yeah, it's probably fine. We'll fix the rest of it. And then they rolled this out across 10,000 post office branches. And what happened very quickly, within days, is that the sub-postmasters, basically the managers of these branches, started reporting discrepancies. They'd get to the end of the day, and they'd say, well, the computer says that we should have this much money in the till, but we don't. Like, the cash isn't there. It's a problem with the new computer system. Now, I want you to put yourself in that scenario. You've just rolled out a multi-billion-pound, 10-year project that's been subcontracted to hell and back across 10,000 different branch offices, and people are saying that the computer is reporting that the amount of money is wrong. What would you do? Because what they did is they turned to them and said, no, the computer is right, the money's missing because you stole it. Give the money back, or we will fire you and prosecute you as criminals. And that is exactly what they did. They started pressing criminal charges against sub-postmasters who weren't paying this back. People remortgaged their homes. People cashed in their pensions, their life savings to pay this money back because they were told if they didn't, they would be fired and they would be prosecuted and they would be sent to jail. This thing has been dragging on for over 20 years now. Now, this is Paula Vennels, the chief executive of Post Office Limited, and she said in the lawsuit that finally came to court that the message the board and I were consistently given by Fujitsu from the highest levels was that while, like any IT system, Horizon was not perfect and had a limited lifespan, it was fundamentally sound. So she's saying in court, oh, we knew it wasn't perfect, but we sent all those people to jail anyway because we didn't want to lose our bonus. The judge, Mr. Justice Fraser. Now, British High Court judges, they never ever say anything vaguely emotional. This is the judge equivalent of like flipping the table and smashing all the windows. He's saying the Post Office defense amounts in reality to bare assertions that ignore what has actually occurred. It is the 21st century equivalent of maintaining that the earth is flat. Now, this finally got to a point of getting some justice and some retribution. There was a case a couple of years ago where all of these people, they had their convictions quashed. This became the one of the biggest miscarriages of justice in British legal history. And all because the people responsible for this IT system, they were not even prepared to acknowledge the possibility that they might have made a mistake. Some people have had their convictions overturned. Some people did not live long enough to see that happen. This Horizon IT system screwed up, it bankrupted them, and they died waiting for the system to get fixed and for them to get justice. Now, I've worked help desk. I know exactly what it is like when the user phones you up and says the computer's made a mistake. You get the phone call, hello, your system's deleted all my files again. Has it, John? Is this like last week when we told you not to put them on your desktop and then give your laptop to your kids? No, it's not like that at all. What did you do, John? I put the files on my desktop. Okay. And John's like, can you check the backups? And you know there's no backups. You know exactly what's happened. But you indulge them. You take a break, you get a cup of coffee, you phone them back. Yeah, John, sorry, mate. We checked the backups, they're not there. Put them on the network next time, like we talked about. You know, this is part of help desk, is you do not have to dig every single rabbit hole until you reach the end and work out exactly what happened. But if the angry user on the other end is saying, the computer says there's £15,000 missing and they want to send me to jail, you check the damn logs. You know, you look at what actually happened. You have to accept the fact that no matter how well you designed and built your system, it is not going to survive contact with reality, because engineering seldom does. Let's talk about two-factor authentication. Brilliant idea, right? Because if someone wants to log in, they need to get your password, and then they need to enter a code that gets sent to your phone. Brilliant system. Works flawlessly, unit tests, integration tests. A friend of mine used to live in an old Victorian house in London which had no mobile phone signal. To get into online banking, she would log in, and she'd grab her phone, she'd run out of the house and run up to the top of the hill and have to hold her phone in the air and wait, and there's the code, and then she had to run back into the house and enter it. Now, does that sound to you like good user experience? Do you think the developers would say that was a bug in the software? Also, no. They'd just be like, well, you live in the wrong house. And you'd be like, all right, you can buy me a house if you want. It is this failure of people anticipating what's going to happen to your code when it gets out into the real world, where things are messy and inelegant and full of surprises. This is a video of the autopilot dashboard on a Tesla going traffic light, traffic light, traffic light, traffic light, traffic light, traffic light. Now, at some point, somebody must have gone, well, how do they transport traffic lights from one place to another? The real world is full of surprises, which is going to catch your software unaware. Sometimes these are failures of circumstance. They are buildings with no network coverage. They are trailers full of traffic lights. Sometimes they are user ingenuity. Users are brilliant. Users are smart. Users are motivated. Users will find a way of solving the problem they have with the tools they have available. A friend of mine used to work for a company who make microscope instruments for laboratories, universities, and they were really paranoid about industrial espionage. And so they had a blanket policy of you could not send attachments by email, not allowed. But they had field service engineers who were being sent all over the world to maintain and upgrade and patch these instruments. And so they came up with a system. What they did is they set up a Hotmail mailbox. And when you needed a firmware update for one of the instruments, you would text or phone your buddy back in the office, and you'd be like, hey, can you send me this firmware? And they would upload it to the drafts folder in the Hotmail box and then tell you it was there. Never send the email. Because if you don't send the email, you can't be fired for sending emails, right? Apparently, they got this system from Al-Qaeda, who used the same thing to avoid government interception. User ingenuity. You give people a problem to solve, and you give them a bunch of constraints. Most users are going to find a way around the constraints. And it's very much down to you how you respond to that. Now, sometimes the way that users violate constraints is wonderful and whimsical and creative. We're just watching Daria's talk there about machine learning and language models, and one of the things that I've been really interested in for my whole career is image recognition and pattern recognition, and things like how does a Tesla know the thing in front of you is a traffic light? Which sounds like it's not that difficult a problem because we have convolutional neural networks. So we take a whole bunch of training data, we run it through the system, and we say, hey, computer, you figure out the difference. You figure out how to tell the difference between traffic lights and fire hydrants or cats and dogs. And the model gets trained and goes, got it. And then you go, all right, let's do something more difficult. How difficult do you think it is to tell the difference between a puppy and a muffin? There are no puffins involved in the sex. Like, it can't be that hard, right? Because we're all humans, like we're super smart. And so this is a classic training data set, is identifying dogs. And I saw a lovely talk a few years ago. Don Wibier was talking about how Azure was now as good at dogs as his 3-year-old daughter. It's like, that's a real dog, that's a cartoon dog, and that one I don't know because it's a picture of the park and the thing in the back might be a dog, which I thought was a really interesting insight. But we can take these same neural networks that have been trained to recognize dogs, and we can use them to analyze all kinds of things. Now, I got this lovely picture of our venue here, the Berzwamba emballage before they put all the scaffolding up on the front. And I ran it through my dog detector, and it said there are no dogs in this picture. But what we can do then, in the spirit of user ingenuity, we're going to take the dog detector and we're going to wire it in backwards. We're going to turn it into a dog amplifier. And we're going to run this picture back through and we're going to say, look, no, trust me, there's dogs in the picture. Enhance the dogs. Find your training data set and crank it up. And the machine's going to go, I'm not sure about this. And we're going to say, no, come on, increase the power. And it's going to go, this is a horrible idea, human. And we're like, come on. And at this point, we're feeding its own training data set back into itself. And so what we get is deep dreaming, which is a completely new and weird kind of art. Now, I'm sure the people who created the neural networks for identifying dogs, this is not what they had in mind. But when the technology gets out there and human ingenuity goes, oh, I wonder what happens if I turn this thing around and wire it in backwards, we get wonderful things. We get art, we get whimsy, and sometimes we get profound sociological change. I grew up in Africa. I was born in Kenya. I spent my childhood in Zimbabwe. And this was my typical childhood holiday, is we'd get in the back of the car and we would drive for 3 or 4 hours along roads that looked like this to some bit of the bush, which as far as I could tell looked exactly like all the other bits, but my parents said we should go there because it was nice. And every maybe 40, 50 minutes along the road, there would be the same thing, a little red shack at the side of the road with the hand-painted logo of the Coca-Cola company. I have no idea how Coca-Cola could get cold soft drinks to everywhere in sub-Saharan Africa in the 1980s, but they did. It was absolutely ubiquitous. Now, I was back in Africa a little while ago. My cousin got married out there, and we were out in Zambia driving around, and it's kind of weird because a lot of it hasn't changed at all in decades. But the little red and white huts by the side of the road are still there. It's just they don't say Coca-Cola anymore. They say Vodacom, which, I mean, I guess it saved buying new paint, but, you know, there has been a communications revolution in Africa within the last 25 years. Now, this is Nairobi, capital city of Kenya. If you went to Nairobi in the year 2000, downtown Nairobi was, you know, a bustling city. It's an economic powerhouse. You've got investment banks and movie theaters. There were internet cafes. There's a couple of people doing web startups and those kinds of things. But you could drive 2 hours out of Nairobi and meet people who had never made a telephone call, let alone sent an email or used a computer. Because wiring Africa was a huge problem. To run a successful telecoms infrastructure, you need 3 things. One is you need a certain amount of population density. If you're going to pay to run 100 kilometers of cable, there need to be people on the other end who are actually going to use it. 2, those people need money. They need to be able to pay for enough services to make it worth your while. And 3, you need a sufficiently stable government and judicial system that A, the government is not going to turn up and say, oh, you need to pay us another 15 million euros because you ran cable without permission. And B, if someone turns up in the night and steals your cable, they will actually get prosecuted. None of these things were true for most of Southern Africa. Very, very sparsely populated country. The people who lived there, many of them are what's called unbanked, like no bank account, subsistence living on cash, subsistence farming, lots of very, very small kind of industry and entrepreneurship. And corruption was rife. Government interference was a big problem for anyone trying to set up telecoms. And a lot of these countries, as bizarre as it sounds, copper is an incredibly valuable commodity. So if you bury 100 kilometers of copper cable by the side of the road and then go home, what do you think's going to happen in the morning? Someone will have dug up the copper and taken it to sell it. Then cellular comes along. Cellular works brilliantly in Africa. We have big, wide landscapes, line of sight. The weather tends to be very dry, very clear. You can put a cell phone tower up on a hill, and that'll get you signal that'll cover maybe 4,000 or 5,000 people with minimal cable, one big cell phone mast. Now, the thing you have to bear in mind about the economics of this is that for unbanked people living in Southern Africa around the early 2000s, a Nokia 3210 was a significant business investment. People didn't have their own phone. What happened is somebody in each village would get a phone, and that would be their business. They would be the phone person. If you wanted to make a phone call, you would go along, you'd give them a little bit of cash, and you would get the phone. They would take your messages for you. You could send and receive SMS messages and things. Now, this is where the user ingenuity comes into play, because almost all of these phones, people don't have bank accounts, so the phones are all prepay. You want to top up your phone credit, you type in the number on the card. Now, a lot of people would leave the villages, they'd go and work in the cities. So somebody's down in Nairobi, they got a job, office, factory, they're working in a bar, whatever, and they want to send money home to their family. And previously, the only way to do this was to take cash, put it in an envelope. Now, if you want to take it yourself, you've got to take about 4 days off work. 2 days to travel there, 2 days to come back. Or you find a bus driver who's going towards your parents' village, and you sort of give them the envelope and ask them to give it to your family when they get there, which sometimes worked, sometimes, and some of the money made it where it was going. But it wasn't a terribly reliable system. Then, what somebody figured out is that these phone top-up cards, you didn't need the card. All you needed was the code on the back. So they could take their 10,000 shillings paycheck for the week, they could go into a Vodacom or a Safaricom store, they could buy a top-up card, and then they could phone the phone person in their mum's village and say, hey, I have 10,000 shillings of top-up for you, and read them the number. So the guy in the village tops it up, bang. They've just invented wireless digital currency transfer. Now, this isn't phone banking because there are no banks involved. What they've done is found a way of using the kind of intrinsic currency of phone credit as a way of transferring money. And then next day, when mum comes in to buy her groceries, the storekeeper's like, oh, I got some money from your son. And she gets her 9,000 shillings because obviously there's a small consideration to be taken into account. Now, this ticks along marvelously for a little while. Then Vodacom launched Friends and Family. And this means you can text people phone credit. You can send someone a message and go, hey, I got 500 credit. Now, of course, everyone in Kenya immediately goes, well, we're all friends and family here. Let's all jump on this system and we'll start transferring currency backwards and forwards. And they bootstrapped a wireless digital economy. People would go to the store, they would pay with a text message. The storekeeper would use the text message to pay the doctor. The doctor would then send another text message to pay someone to fix their bicycle. This system went round and round and round. Now, somebody at Vodacom has got to be looking at this and being, this was a disaster. Like, we rolled out all this mobile phone infrastructure in Kenya, and they're not making any phone calls. And they're not using any service. All they're doing is texting each other credit backwards and forwards. And you can imagine a certain kind of management board who would have closed down the entire project and said, this was a failure, and yeah, we're not going to do this. That's not what they did. Vodacom and Safaricom got together, they turned this into a product. M-Pesa, M for mobile, and Pesa is the Swahili word for money. They trained a network of M-Pesa agents, so you could go into one of these stores with your phone, and you can be like, look, I got this much credit, you send them a message, they give you cash. So you can go and pay your wages or buy groceries, all these kinds of things. M-Pesa became the de facto banking system across the whole of Kenya. And it was the right thing at the right time. And it's a really interesting outlier. Uganda, Tanzania, they have this a little bit. They tried to launch it in Romania in 2014. And Romania went, nah, we don't need that. We'll have Visa soon. And they were right. Visa rolled out there. They rolled out M-Pesa they rolled it out in Afghanistan during the US occupation there. And one of their biggest successful contracts was the Afghan police force decided they were going to use M-Pesa to pay all their salaries. And what they discovered is that 60% of the police officers who were on the Afghan payroll did not in fact exist. Because the sergeants had been going, oh yeah, you give me all the cash and I'll pay all the officers at the end of the week. And then they roll this out and they're like, we need contact details for all your officers. They're like, oh yeah, well, this one just retired, or this one ran away, that one must be sick, we don't know what's happened to him. In Kenya, M-Pesa survives today. It's absolutely revolutionary. Having a secure way to earn money, store money, transfer money represented a path out of poverty for something like 250,000 families. And all of this because they engineered a system, they deployed it, and the end users looked at it and went, no, we're not going to use this the way you designed it. We've got a much better idea. Now, when you go out, you design systems, you deploy them into the real world, remember your users are ingenious, they have stuff to do. Fight that urge to go, no, you're doing it wrong. Watch them, learn from them, because they are going to come up with solutions to their problems, which you can then incorporate into the work that you're doing. Never, ever be arrogant enough to go, this is wrong, it doesn't work, or this system is bulletproof. It is absolutely fail-safe. There is nothing that can possibly go wrong with it. Let's go out there, let's build awesome stuff, let's give it to users, and let's celebrate the weird and wonderful stuff that they are going to do with it, because failure is always going to be an option. Thank you.